Hey guys, how's it going? Mike coming back at you here with another video on number theory. In the previous video, we did a little bit of an introduction into some notation that you're going to be seeing popping up frequently throughout this course. We got you used to some special symbols as far as names for sets, some set notation, and then we also went through some proof strategies. Just looking at how do you prove statements that fall into one of a couple particular forms. And we talked about several ways that we can prove those things there. Today we're going to get into the first topic in number theory, mathematical induction. If you have taken discrete mathematics and or techniques of proof before, you will probably have seen this. So this may just be a little bit more of a review, but still hang with me, listen in, watch. It never hurts to go back through old stuff. If you haven't taken discrete mathematics or techniques of proof, then this will probably be something new. So hang around and listen in and watch. So first of all, mathematical induction is one of the easiest and nicest forms of proof to sort of kick off your experience with proving mathematical theorems and mathematical facts. It's a nice three-step process. We'll get into each of those three steps, what they're doing, what you have to do in each of those three steps in the technique of mathematical, or of proof by mathematical induction, I should say. But you probably have not, perhaps you have not seen or heard of the mathematical principles that, the mathematical principles that are really operating behind the scenes here. You may not have seen or heard about what's really letting us say that mathematical induction is a valid form of proof. And that background mathematical principle is this thing called the well-ordering principle. And what the well-ordering principle says is every non-empty set, which we'll call capital S, of non-negative integers, so whole numbers that are non-negative, contains a least element, a least guy in there. That is, there exists some integer a in this set S, such that a is less than or equal to b for every guy b that's in this set capital S. And when we use mathematical induction to prove some facts, the question will kick off by saying, for n greater than or equal to some number, the number that would be in the blank is where we'll start at. And this guy corresponds to the A in the statement of the well-ordering principle. Just as a quick side note, you can prove, or you can take this principle and you can use it to prove what's known as the Archimedean property, and you can prove it by contradiction. The Archimedean property says if a and b are positive integers, then there exists some positive integer n such that na is greater than or equal to b. I'm not going to go through the proof of this in this slideshow here. The proof is in my notes. If you want to look at the proof, you can go look at it on there. But from the well-ordering principle, we get what's known as the first principle of finite induction. And this thing forms the basis for mathematical induction. And this thing really lets us say, okay, mathematical induction is a valid form of proof. Here's what the first principle of finite induction says. Let capital S be a set of positive integers such that two properties are satisfied. One, Property number one, 1 is in S. And the second property that holds is that when K is in S, K plus 1 is in S as well. Then, if those two things hold, then capital S has to be the set of all positive whole numbers, the set of all positive integers. And if we think about this for just a short time, we can see that this makes sense. Pretend that each of your positive whole numbers is a domino, and you lined all these dominoes up. You stood each of them up and you set them all up so that they form a single straight line that would go on forever and ever and ever. Property number one, saying that 1 is in S, you can think of that as you knock down the first domino that you had stood up. The first domino that was stood up in that line, you knocked that guy over. And property number 2 says that if you know that you have a particular positive whole number in your set S, then you know that the next guy is also in your set S. Comparing this to our dominoes being set up in a straight line, basically what property 2 is saying is that when you knock one over, you're guaranteed to knock over the next guy that is in line. So if you knock over the first guy that's in that line, and you also know that when you knock a guy over, you're going to knock the next guy over, when you have these two things, you know that you're knocking over every single domino that you have set up in this line. That is to say, you know that this set S has to contain all positive whole numbers. So we can take this really possibly seeming as basic, yet also very, very important, and possibly seemingly very, very confusing mathematical principle, and we can tie it into something that's kind of fun. And the first principle of finite induction is really the basis, or is essentially mathematical induction itself. When we see a problem where we have to use mathematical induction, the problem will always be phrased something like this. Prove for n greater than or equal to some positive whole number a, some statement capital P of n. The 3 steps that you need to do to prove this statement, P of n, using mathematical induction, are as follows. First thing you have to do is show the basis step, this is called. You show that P of n is true for n is equal to a. These statements P of n, these are usually equations, something involving sums of numbers or certain numbers raised to certain powers are typically equal to some nice formulaic quantity. There are also cases where it is a quantity is greater than or equal to some other quantity or something like that. But for the most part, we'll be working with problems where something is equal to something else. And what you're doing in this basis step is you're taking your a value, you're taking that first value that you have to verify, and you plug it into both sides of your mathematical facts, and you show that the left and right hand sides are equal to each other. The basis step here, showing that P of n is true for n equal to a, corresponds to property number 1, in the first principle of finite induction. In the statement of this principle, it was 1 is in S. For mathematical induction, we're showing that A is in S. Really what we're doing here in our basis step is we're showing that the first domino gets knocked over. The next step, and which is just a simple statement, but you're going to use the second step in our third step of this three-step process. The second step is known as the hypothesis step. And this step is always just a statement. And the statement is always assume that the statement P of n, I should say the equation P of n that we're given is true for some arbitrary or random positive whole number k. Step 2 is always just a single sentence that says assume P of n is true for some arbitrary positive whole number k. The third step involves the most work. It is the most confusing. It is the easiest place for people to get tripped up when you do problems or when you prove things using mathematical induction. This is known as the induction step, and you have to show that the statement that P of n, you have to show that that's true for when n is equal to k plus 1. And always in the induction step, you're always going to be using your hypothesis. You're always going to be using that statement that you've assumed in the second step, in the hypothesis step. And you always use that thing pretty much right off the bat. Now, we said that the basis step in this three-step process of mathematical induction corresponds to the first property in the first principle of finite induction. Properties number 2 and 3 here, the combination of those is the equivalent of property number 2 in the first principle of finite induction, saying that when k is in S, k plus 1 is in your set capital S. Step number 2 here, the hypothesis step. This is the when k is in S part. And step 3, which is your induction step, that is showing that corresponds, I should say, to the k plus 1 is in S part of your first principle of finite induction. So we can see how the first principle of finite induction is basically, essentially, the exact same thing as this three-step process needed for mathematical induction. And when you have shown or performed all 3 steps and you've shown that they are true, then you can just nicely sum it up with thus the statement is proved via mathematical induction. So this was a whole lot of talk, a whole bunch of detail on the proof technique of mathematical induction, the math behind it, what is going on here. A lot of just general mathematical facts, connecting things. In the next video, we're actually going to go through some sample problems, and we're going to see how we use this proof technique to prove some mathematical facts. If you have any questions or comments, be sure to drop them in the comments section below. Otherwise, until the next video, take it easy, guys.